So welcome everybody to this IOP symposium, which is about the work that we are currently conducting about connecting to the networks of the human brain by real-time EEG-guided closed-loop TMS. This symposium, the idea of having this symposium came under the umbrella of the Connect to Brain European project, an ERC synergy project, which has as PIs Risto Moniemi, Ulf Ziman, and Gianluca Romani from the universities of Aalto in Helsinki, Tübingen, and Chieti, respectively, in Germany and in Italy. So today we will first, under this umbrella, cover the idea of designing a new tool for stimulating the brain, which we call the Multilocus TMS. And with this, we will be able to stimulate different sites of the brain and to monitor at the same time the status of the brain through EEG, and use the EEG data in order to again stimulate the brain informed by the changes that have occurred due to the previous stimulation. So this is the big umbrella, and the idea now is to put together the effort of the hardware part, of the software, of the clinician, to understand where, when, and how to stimulate the brain in order to have the maximum therapeutic impact in the long term. So today, each of us will cover one of the specific aspects of the project, and Timo Roine from the Aalto University will talk about the development of this new system, the Multilocus TMS system. Then Christoph Trenner will talk about this idea of using the EEG information in order to simulate the brain in a closed-loop fashion. Then I will more specifically focus on the idea of using functional connectivity derived from EEG in order to inform the stimulation or to link the stimulation to the effects that it has on the brain. And finally, Pantelis Lumis will talk about the assessment of a specific network, which is the human cortical language network, for the presurgical evaluation and for basic research purposes. So, of course, this is the whole consortium which we want to thank before we start. And then I leave the floor to the first speaker, which is Timo Roine from the Aalto University.
Thank you, Laura. So let me share my screen first. Okay, so I will introduce the development of the Multilocus TMS system. Majority of the work is being done in Aalto University, but of course all of the three groups are participating in this work. So first I will shortly introduce TMS, transcranial magnetic stimulation. So with TMS, we can activate the brain non-invasively and painlessly through electromagnetic induction. And it is used for presurgical motor and language mapping and for treatment of neurological and psychiatric disorders, for instance, depression. However, the current technology has several limitations. It can only be used to stimulate a single location at the time. And changing the locus of the stimulation is very slow and operator dependent, so this is done typically manually. It is also blind to ongoing brain activity, and these limitations might affect the relatively low therapeutic efficacy of the current treatment protocols. However, with Multilocus TMS, we will use multiple coils to be able to stimulate and electronically move the stimulation locus. This enables many other applications. For example, automatic mapping of brain behavioral relationships and connectivity. It also enables more complex and individualized multilocus and feedback control paradigms. In addition, the protocols can be performed faster because of the automation, and the user dependencies and operator dependencies are eliminated. So for most effective protocols, both for treatment and research, we need to stimulate the brain at the right sites and times. What is needed to do this? We need multilocus TMS to electronically move the electronically control the locus, direction, intensity, and timing of the stimuli. In addition, we need real-time closed-loop system and algorithms to be able to characterize the brain state, activity, and connectivity. However, most importantly, we need to translate all of these methods into clinical practice to have a real effect. Next, I will show this is an illustration by an artist what the final system might look like. So here we first showed the moving automatically, and now showing an example of stimulating multiple targets at a time. In addition, we can do closed loop stimulation activity. So the Connect to Brain project consists of 3 parts, and all of these work together towards the final goal, which is multilocus TMS therapy. And these parts are very closely linked together. For instance, we need neurophysiological models to know what kind of brain state we need to reach to be able to develop these closed-loop algorithms. So next, I will talk about how this multilocus TMS device is actually built. So our approach is to increase the number of TMS transducers by placing them over each other at the first stage, and later we will also be placing them adjacent to each other. But this way, by placing these 5 coils on top of each other, we have each of them has a basis function, which are shown here below. By combining these basis functions, we can move the locus of the stimulation millimeter by millimeter, also change the direction of the induced electric field. The first prototype, as shown here, will consist of 5 coils, and with these we are able to move the locus of the stimulation within an area of 3 by 3 centimeters and change the direction of the electric field freely. However, the final prototype might contain something like 50 coils to be able to, and then it would be able to stimulate almost anywhere on the cortical surface. In addition to the coils, we need electronics to control them. These electronics are based on H-bridge circuits that are able to drive pulses with less energy and less coil heating compared to conventional TMS electronics. In addition, we are developing high voltage pulse transforms, which can be used to approximate lower voltage pulses and thus avoid the need to discharge the capacitors between the stimulations, and thus enable faster pulse trains. In short, the final closed-loop system should be able to measure and predict the brain connectivity and state, and control the brain towards the desired state using a real-time artificial intelligence system. So we could use MEG and fMRI-based priors, but also structural connectivity based on diffusion MRI as a prior information to the system, but the main real-time information would come from the EEG. The software architecture that is being developed is a microservice architecture implemented with Apache Kafka. And the benefit of this is that it has a high throughput and low latency, which are desirable properties of this kind of real-time system with high dimensional data and high frequency. Other benefits of this system is that we can have all of the information automatically logged, and that would enable also recording and playing back the experiments afterwards. In addition, this kind of microservice architecture enables us to use different programming languages. So different modules in this system can be programmed using different languages. For example, some algorithms can be in MATLAB and some in Python and so on. And we have also performed user experience research to find out what kind of user interfaces we should develop for this system. And this is an example of the user interface for an automated target search algorithm. And pressing the start button in this interface would begin the automatic search, and the user can observe the process using these markers that are shown on the cortical surface. And this is the algorithm for the automated target search developed by al. So as we are able to electronically control the stimulation location and orientation, we can develop this kind of automated algorithms for the target search of the motor hotspot, but also for other hotspots. These provide an operator-independent way to find target, like target locus, but also the target, the best orientation to for this specific target. And this example shows all of the stimulations with the circles that have been performed to find the hotspots marked by the X. In addition, real-time cleaning algorithms for the closed loop e.g. TMS have been developed. This real-time algorithm consists of two consecutive spatial filters. The first filter removes ocular artifacts based on the ICA, independent component analysis, using short calibration data that has been measured before the actual experiment. The second filter then removes noise signals that are not likely to originate from actual intracranial sources. And this filter, called sound, is constantly updated on the background and is able to detect and clean automatically the bad channels during the experiment. And this has already been tested in like true real-time setting. Its data sample was cleaned in less than 0.2 milliseconds. Here's an example of the results. Aidokan et al. Have been also developing this kind of real-time tractography-based neural navigation. So with this approach, the streamlines describing the neural pathways of the brain are reconstructed in real time during the experiment. Of course, prior to the experiment, the subject has to have undergone MRI and diffusion MRI specifically to be able to reconstruct these streamlines. So real-time information about the structural connectivity has a great potential in improving the targeting of the TMS. So current MTMS transducers are quite heavy, and they will become even heavier in the future. So with the 5-coil, still possible maybe to operate the coils manually, but because of the larger prototypes, we are already looking into the robotic guided MTMS, And the benefit is that this robotic control could be used to automate the placement of the MTMS transducer over the target region. And it also it can be used to compensate for the slow movements of the head and move the transducer to target regions where the electronic control cannot reach. So in this prototype, if we want to stimulate further away from the original site than 3 centimeters, we would need to move the transducer mechanically, and this robot could perform this. So this way we can improve the flexibility of the MTMS without compromising spatial accuracy and automation capabilities. So in conclusion, the new Multilocus TMS device enables automatic control over the locus, direction, intensity, and timing of the stimulation. In the first prototype, this means that the target region would be something like 3 by 3 centimeters. It also enables stimulation of multiple sites simultaneously or with millisecond scale delays. The system also enables individualized feedback control protocols based on real EEG. And we can also use automatic control algorithms to find targets faster and reduce user-dependent variability. So what all of this means? So this is causing a paradigm shift in psychophysiology experiments as well as in treatment, and there is huge potential for improvements in the efficacy of the TMS. And I would like to thank all of the hardware software group working towards this system. Thank you.
Okay, so thank you very much, Timo, for your presentation. So our next speaker today is Christoph Trenner from the University of Tübingen in Germany, and he will talk about EEG brain state dependent closed loop stimulation. So please, Christoph.
Yeah, thank you. Thank you very much, Laura, for organizing this symposium. And I want to start by introducing two enemies that we have to turn into friends. And those enemies are EEG and TMS. So this is what EEG and TMS recording looks like if you measure the EEG during the TMS pulse. And these lines, they are the artifacts from the TMS, just looking at raw data. This is 4 pulses, 4 artifacts. And at this level, you don't see anything useful. And this is one of the big challenges that combining EEG and TMS has. So let's zoom in on one of those. And we're going to look at the easier part in this talk, which is the part before the TMS pulse. So this left side. But of course, the evoked potentials of the EEG are tremendously important for the Connected Brain project too. But as I said, let's focus on the part on the left. This was just a very brief introduction in the topic of using EEG. This is what it looks like to improve the effects and the therapeutic effects that we can have with TMS. So now we go back to a more beautiful looking description of the issue, which is if we stimulate here at the first flash with the TMS pulse at the positive peak of this oscillation, do we get a different therapeutic effect than if we stimulate in the negative peak here of this same oscillation? And that's really the guiding question behind the brain state dependent TMS. So we'll talk a bit about this idea that fluctuating oscillatory brain states can become therapeutic targets. So not only in terms of where we stimulate, but also when should we stimulate to get the therapeutic effect that we want. Then we will talk a bit about excitability and plasticity, practical issues, briefly about clinical applications, and then how this fits into the current really interesting and important developments of this project. Okay, so what evidence do we have that these fluctuations in the oscillation actually play a role? And this is really the main result that gives us confidence that brain state gives us a window to what the cortex is doing in terms of excitability. So this is just after the experiment with 1,000 pulses, sorting each pulse into a phase window. You can see at the bottom there's a negative peak, positive peak, and so here we go. So this would, for example, be the average pre-stimulus EEG. So here we're in the negative peak, so that's this phase spin, and then the positive part here. And then we can look, is there an effect on the response of the brain when we simulated that at that state? And this is the y-axis, which is the amplitude of the evoked motor potential, which you can measure, the twitch of the hand. And it does turn out that if you then look after the experiment, you sort each trial, that if you stimulate it during the negative peak of the mu rhythm in the motor cortex, you get larger evoked potentials. Now, of course, this is a subject where this worked very beautifully. It's not always like this, but this is the idea that we have these periods in the brain where excitability is higher, and then we can build this kind of a real-time setup. So this experiment here, you don't need a real-time setup. You can just stimulate randomly and then sort the trials afterwards. But now if you want to stimulate reliably in one phase, you need a setup that does analyze EEG in real time. And this is the method that we built, filtering the data and doing a forward prediction and then triggering the stimulator at the appropriate time. And if this is true, that there are these periods that are windows of opportunity to induce plasticity in a specific way during the high excitability phase, then it looks like there would be these negative phases. And here again is just some data to show the difference in the evoked potential, negative versus positive. But now the question is, if we stimulate in the negative phase, do we get different plastic effects? And yes, we do. And this, I think, is the more important result for the purpose of therapy. If we stimulate repeatedly in this negative high excitability phase, we get long-lasting increases in excitability here for about half an hour. And it actually looks like these periods are very short. So if you stimulate randomly, you will stimulate in the peak excitability phase sometimes, but it looks like it's a short part of the circle, and here the random phase stimulation is much closer to the effect of positive stimulation than stimulating here during this period. So it does seem to be important. This is what the setup looks like. If you add a second coil, and then we can move to really modulating pathways. And this is just an experiment where we looked at is there a difference in the intrahemispheric connection during different phase states. I won't explain this in detail, but this is some of the motivation of why functional connectivity is going to be critical to go to this next step of modulating pathways. Okay, now some practical problems. If we're estimating brain state, I think this is something that a lot of us, and especially myself, completely underestimated when we started this kind of research many years ago. The difficulty of really understanding what we're measuring and what it means, because the challenge, especially if you're coming from a clinical side, you put the EEG, you think, okay, you get the oscillation, but there's a lot of assumptions, and there's a real problem of mapping the activity that's really inside the brain at the area that we're interested in to the measurement we get from combining the many EEG electrodes in some form to get this oscillation. And I want to just explain a little bit about these two steps. And the first is to extract the signal to decide on what we call in the clinic the montage to extract a specific brain signal, and then the question of how to estimate the state at that moment. And really, it's a question of spatial filters. We tried many different ways. The motivation is that if you move the electrodes a little bit, just because you're shifting the cap, for example, you end up measuring a different signal, even if this is only a centimeter or an inch further anterior. The oscillation that you get is shifted in phase. It's a different mix of signals, and it's very difficult to decide what is the appropriate oscillation and the appropriate montage or spatial filter to use in that specific individual, so that the thing that you're measuring on the right corresponds to the real signal inside the brain. So it's very hard to know when what you're measuring is actually measuring something physiologically relevant. And here is just a data set now looking at 55 participants, where we compared a montage around the electrode C3 versus the neighboring electrode, and you can see that it makes a big difference. It looks like C3 works on average quite well, and the neighboring electrode FCC3H in the high density EEG cap does not. So this got us into thinking about how can we improve and personalize the extraction of signals. We looked at different montages and the EEG cap, and individualizing filters with functional methods, with beamforming methods. Here's a quick result that shows that yes, you can get a little bit better using, in this case, fist clenching as an input to improve extraction. Again, I think I just want to raise this issue without going into the details of all these studies. And then the anatomical method, where we say, okay, well, if we're interested in a specific area of the brain, why don't we model this and then calculate the optimal EEG montage to extract a signal from that specific area. And this has been working quite well, but it's quite a labor-intensive process. So we're not yet at the point where we can strongly recommend a specific method. The surface Laplacian, the method that is in some ways the simplest, actually works surprisingly well, and it's still a method that we use primarily, even though we are convinced that it can be improved. We don't yet know how. So, and this is only the first part. This is the first part of the problem. Now we have the signal, and now how do we really characterize the signal in terms of estimating just simply phase? This is tricky, because you have to choose the appropriate filters. You have to now time filters in time, and also making sure that the oscillation is actually present in the signal. This can be a conflict with deciding the spatial filter, because if you're focusing on an area of the brain that doesn't express the oscillation that you're interested in, then you have a low signal to noise ratio, and it's hard to estimate phase. Again, sort of going briefly into this problem, where we only have the data. If the red line is the time we want to stimulate or decide to stimulate, we only have the data on the left. We have to predict it, and how accurate can we be from just the data ahead, sort of the data in the past. We looked at more than 100 participants to try and understand what are the factors that affect the accuracy that can be achieved. And it turns out that the main factor is signal to noise ratio of the oscillation. Here on the right in the rows plots, you can see the spread of the phase errors that are estimated. And if you have the oscillation in a high signal to noise ratio, and if you stimulate during periods where the amplitude of the signal is high, you can get very nice targeting. But if either of these conditions are violated, you're really not stimulating very accurately. So those are the two points in terms of spatial and temporal signal extraction. And one additional issue here is, or just illustrating here, the concept of signal to noise ratio, where you have the dotted line, the 1/f background activity, and then this difference pointed out by the arrow in decibels, how much more power is in the oscillation of interest versus the background noise. We then looked at where different oscillations are coming from. This is a brain at rest, and we can see that there is a theta oscillation at sort of 6.7 hertz located in the mid-frontal region. There's a occipital alpha here in the middle on the right, and then there's the sensory motor mu alpha. There's a beta oscillation, there's a harmonic of the mu, and then there's a 28 hertz frontoparietal oscillation, which seems quite interesting, but we don't really understand how that comes about yet. So these are then the possible therapeutic targets. These are the easy oscillations to get at. The patient is sitting there. These are the oscillations that are present on the brain, and we can put a coil there and decide to stimulate at a particular phase of that oscillation. So just to give that that view. Now, what are the possible clinical applications? The easiest is to think about where TMS is used today. So neuropsychiatric disorders, stroke and depression being the main ones. And at the University Hospital in Tübingen, we looked at applying this method of EEG trigger TMS in both of these conditions. This was a study in 17 patients with major depression, a pilot study, just to investigate feasibility of targeting the dorsolateral prefrontal cortex alpha oscillation and comparing negative peak versus random phase stimulation. This was not a therapeutic study, it was a single session that the patients received, but it was real patients that suffered from depression at the time. And we used the resting EEG as a proxy for did we manage to change excitability. We did get a significant change in the resting EEG, indicating that the negative peak triggered TMS did have differential effects on increasing excitability. So this is promising, and the follow-up larger study will hopefully be starting soon. So just a very quick overview over the depression application, and then of course stroke. This is a study currently still running at the neurology hospital in Tübingen, where we have a total of 30 patients that are randomized into a group receiving phase-triggered negative peak motor cortex stimulation over the affected hemisphere versus a control group receiving the standard treatment, which is over the healthy hemisphere. And I don't have preliminary data yet. I just want to show you that these clinical applications are ongoing, and we expect to finish this study later this year. It was obviously delayed due to the pandemic, but let's see how this will continue in larger studies that are planned, and that I think will be very exciting. So where does this leave us? What does the current data and results and studies mean in the context of this larger Connect to Brain project? And I think these are sort of building blocks of really understanding the goal of neuromodulation as not just changing a particular area in terms of excitability, but modulating a whole network, and doing it in a personalized way where every stimulation is different. There are no standard protocols, but there's the optimal stimulus to change the specific brain in a specific way, looking at the whole network. That's obviously the goal. And I think Connect to Brain is a fantastic project, both in terms of methods, technically and analytically, but also clinical applications. And I'm very excited to be a part of this project. Take-home message: EEG, we believe, can help us define therapeutic targets. Phase and amplitude of oscillations is a start. This real-time multilocus method can solve both problems of where to stimulate and when to stimulate. And I think the important research topic is how to move to this individual pathway-specific neuromodulation, which clearly requires an understanding of brain connectivity states. I think this is the perfect time to end and the perfect sentence to end my talk on, because there's no one better than Laura to share with you where we are, where the project is, where Laura is and her group on understanding brain connectivity as a more advanced therapeutic target than simply the phase of oscillations, which is where we are today. And with that, I thank you for your attention.
So thank you, Christoph, for your nice talk. And thank you also for the nice introduction, which brings me to my talk, which is indeed related to the first steps that we did in using functional connectivity derived from EEG in order to to use this into this closed loop environment and to drive the TMS device and the multilocus device in the long term. So basically we are working on this part of the project, which is to derive real-time EEG or time result in a larger sense, EEG connectivity, in order to use this for understanding, as already mentioned, when and also where to stimulate the brain in order to derive our goals. So, but why functional connectivity, and specifically which functional connectivity are we looking at in the project so far? So the kind of functional connectivity is closely related also to what Christoph was discussing. So the idea is that phase is an important information in the brain, and that this not only somehow characterizes the excitability state of one brain location, but that also plays a role in the coupling between different brain areas and regions. So the large theoretical framework is that of the communication through coherence hypothesis, according to which if we have two brain regions, the red and the blue one, for example, and they exhibit two oscillations as depicted here, if these oscillations are more or less synchronous, so if they have their peaks and valleys which are aligned in time, so this gives to these two regions the opportunity for exchanging information. On the other hand, if the blue and the black one have, in this extreme example, counterphase oscillations, then this will mean that these two regions will not have the possibility for firing together and so sharing information somehow. So a lot of measures in the EEG and MEG and the electrophysiological at large community have been developed in order to catch this information that is contained into the signal that we can measure non-invasively. But all these measures, as long as they concern to phase coupling, have something in common. So what they look at is the consistency across time or trials, depending on the situation in which you are, of the phase difference between two regions. Like in this rightmost part of the slide, you can see the red and blue situation depicted in terms of phase difference, and this rose histogram depicts the phase difference across trials, which you can see is somehow clustered along the one main direction. If, on the other hand, the blue and the red, for instance, regions are not coupled one to the other, so that means that when we will look at the phase difference across time, we will see something that is scattered around 60 degrees circle, so as in the bottom case. So, and this is really, without going into the mathematical details of the methods that we use, but this is really the common foreground and playground of these metrics. And we want to use this, this phase difference between the areas in order to try to understand when to stimulate, and if this relationship of phases between different brain regions now plays a role in the effect of the stimulation that we will deliver to the brain. But before doing that, we need to understand how it is possible to do this in real time, or quasi real time. So what is the limit that we can reach with estimating functional connectivity from EEG data in terms of looking at small time steps or time beats. So before we go into the application, I also need to advise about some pitfalls that one can encounter, not only when estimating phase itself, as Christoph did, but also when looking at phase differences between different brain areas. So let's suppose that we have two toy examples. The top one is an example in which our two oscillations, the blue and the orange, are phase coupled, and the bottom one is one in which the two oscillations are not phase coupled. And if we have the possibility of using the full amount of data, which in this case is about 1 second, in order to estimate the phase difference, then we will nicely see that the phase difference of the uppermost case is really peaked along one direction, whereas the phase difference of the other situation, so the uncoupled situation, is scattered around the circle as we were expecting. Nevertheless, if we now imagine that we can only look at this coupled and uncoupled oscillation through a small window, then the thing becomes harder. Because in the first case, okay, we are still fine, and we might get the phase difference that we would get also if we had the full amount of data. But also in the lower situation, what we will have is not a phase difference which is scattered around the circle, but we will have some deviation from the main direction, but still it might become hard to say whether that's just noise that makes the phase difference not so peaked along one specific direction, or whether it's really the fact that you are only observing part of the signal. And so what we wanted to understand is, okay, what is the best that we can do in terms of studying this phase coupling using different connectivity metrics when we only can look at one window of our data, because we want to do it in real time, so meaning that we want to do it while the data are streamed and acquired from the EEG system, and we can only have at our disposal a small amount of data. And okay, this is, I won't go into the details of this, but say this is simulated data, and all these like labels that you see here, they mean different, slightly different metrics that are commonly used in the community to assess functional connectivity. And what we did is to derive these coupling measures, both from an approach based on Hilbert transform and on Fourier transform, which are basically the most common and widely used. And we simulated different situations of signal to noise ratio. And specifically what we did in the simulation was to generate our data and then back project them into the, onto the brain and take the signal to noise ratio of the projected data. Anyway, so the take-home message of this study that is still ongoing is that first of all, if we have at our disposal a small window of data, then it's somehow more reliable to use Hilbert-based approaches to study functional connectivity, regardless of the specific method that we are using. And that you can see it from here, because basically already with 5 cycles of our oscillations, you can get some, area under the ROC curve, which is quite high for the most of the methods that we have at our disposal. If we then shift to the lower row and we use Fourier, then you can see that with the same amount of cycles, your ability to recover the coupling is much lower. And the other take-home message is that overall, of course, somehow it depends also on the signal to noise ratio that you have, but say that you have something around 10 dBs, which is a reasonable signal to noise ratio for the data that we are working with, then basically all the methods will work reasonably with a number of cycles, which is between 5 and 10. So this means that if our oscillation that we want to study in terms of coupling is, for instance, the mu rhythm or the alpha rhythm that we were talking about before, so which is 10 Hz, then the length of the time window that we will need in order to reliably assess functional connectivity is something between 500 milliseconds and 1 second. So, but in this simulation, we simulated the ideal situation in which our connectivity between the two regions is always on. So it's not something that is changing with time, it's always up, and we only have this window through which to look at this connectivity state, which is always up. But what happens if, as it is likely in the brain, then the connectivity is not always up, but also the connectivity varies with time. So basically, in this case, you can see that we simulated the duration of the connectivity state as the step length. So in this case, you have a connectivity between two regions that is lasting for 1 second. And then when you move towards the right, the connectivity, the duration of the connectivity state is shorter. So the minimum value that we simulated is 125 milliseconds. So now we have two windows. One is the window of the actual connectivity, and the other one is the window that we are using to sample this connectivity. And basically, if we have to take an overall message from this simulation that we have done, the overall message is that as long as you have a window that you use to sample your data that is shorter than the actual connectivity state, that is super fine. So for instance, let's imagine that we have the opportunity to look at our connectivity towards a 500 millisecond window, which is the green row. Then we will be able to nicely represent the connectivity lasting 1 second and also the connectivity lasting 500 milliseconds, still with some, reasonable result. We could be able to look at something which is around 250 milliseconds, but then if anything lasts less than this, we are completely lost, and our connectivity step completely is lost within the noise shaded trace that we have in the picture. So now the next question would be, okay, so if we have to use windows, which are, as we said before, between 500 and 1,000 milliseconds, so in 1 second, this means that we will equally be able to nicely appreciate something in the brain that has more or less the same duration. So the question is whether this connectivity, there is a connectivity in the resting brain, for instance, between the two motor cortices that has this duration. And a recent study by the Tübingen group, they showed that indeed, yes, not all the connectivities in the brain between these two regions have such long-lasting duration, but still about 1/4 of the connectivities is long enough to be captured by the approaches that we are using. Of course, more needs to be understood about this, but still this makes us confident that we will be able to to see something in real time, which is coupling between different brain areas. But now the question is, okay, so say that we can really nicely sample this connectivity also in real time, although with some limitation, then would this connectivity have anything to do with the effect of TMS pulse that we will deliver, like Christoph has nicely shown for the phase of one location? So in order to understand this, to data from the project acquired by the Tübingen group. And these data are EEG data of resting state, also the period before the TMS pulse, so basically the same period that Christoph was showing in the very beginning of his talk, and looked at whether the effect of the TMS pulse in terms of corticospinal excitability as indexed by the motor evoked potential amplitude at the muscles like of the end of our subjects is somehow affected by the status of the connectivity before the TMS pulse. So in order to see, to understand this, we took, as I said, this period before the TMS part and estimated the functional connectivity with one of the metrics we have seen before between the left motor cortex and the rest of the brain. And so the one that you are seeing now is an average across all trials, which are about 1,000 for each subject and all subjects. And this is connectivity at the frequency of the mu rhythm, which was identified subject by subject. And okay, this is basically the same view from an orthogonal perspective. So overall, the first statement that we can make is that, okay, so there is somehow consistent connectivity of the left motor cortex to other regions which are nicely belonging to some kind of motor network at the frequency of the mu rhythm. But this is true across all subjects and all trials. So what happens if we now pick one subject and look across all trials? Is this something that is changing trial by trial? Or is this something that is there in the brain and no matter what happens and how time passes by? And the answer is no, okay, this connectivity trial by trial. So every time we take one piece of data before the TMS pulse, this connectivity of the left motor cortex to the rest of the brain changes, still continues to enroll other regions which belong to the motor network at this frequency, but still, as you can see, sometimes it's higher, sometimes it's lower, sometimes it's recruiting more regions in the opposite hemisphere, and sometimes more ipsilateral regions, and so on. So the question that we that we asked ourselves, hopefully will be answered extensively also in the future, but the question that we posed and we are starting to answer so far is whether this coupling between different brain regions has anything to do. The coupling that we are seeing, it changes and varies from trial to trial. Does it have anything to do with the changing of trial by trial corticospinal excitability as indexed by MEPs? So in order to understand this, we also did some MEP modulation, calculated some MEP modulation, very similar to what is usually done for the face. And so what we observed is that, for instance, if we pick the first two bars, this is average across subjects, and splitting the trials subject by subject in trials with low connectivity between the left motor cortex and the left SMA, or for instance, high connectivity between the same left motor cortex and the SMA. And we can see that if we split subject by subject trials into these subgroups, we see a difference with respect to the average value. We see a difference also in the amplitude of MEPs. So the higher the connectivity, the larger the MEPs. This is true not only for the connectivity between left M1 and SMA, but it's true also for the connectivity between left and right M1. With the actual statistical significance. You can also see a tendency if you look at the connectivity between the left motor cortex and the right premotor cortex, although this did not reach, at least with our sample, which is not large, although the number of trials is very high for each subject, did not reach significance. But then we asked ourselves, okay, so we could look at these regions independently, but if this act as a network, then maybe if we put together the trials in which both are high, the connectivity between the left motor cortex and the SMA, and the connectivity between the left motor cortex and the right motor cortex. So if we put together, like subsample the trials and pick only those in which we have not only one pair connected, but for instance, two pairs like in more network-like fashion, then what happens to this MEP modulation? And the answer is that the MEP modulation increases. So basically, when the full network is in those trials in which the full network is connected, then this modulation of the MEPs is even larger than in comparison with the situation in which only one pair is connected in the network. But then, as you have seen, the idea is not only, I mean, to show, which is nice, that at the group level we have this effect, but also to use this in a personalized way and individualized way. So we need to understand whether this connectivity can be helpful in predicting the MEPs also in the single subject, in the individual subjects. And okay, what we did, I mean, to use a linear regression model and see whether both the phase and the connectivity were basically predicting the MEPs in the same way, or if one or the other could add something on top of the other measure. And I mean, overall, the idea is that the phase, the local phase, and the connectivity do not really catch the same information, because sometimes in some subjects, if you also use the motor network connectivity, this improves the MEP phase-based prediction, and sometimes it's just the opposite. So the phase prediction at the left motor cortex or C3 improves the connectivity-based prediction. Here, actually, everything is done in source space, but I mean, it's similar to what we have seen also done in the other montage, like the C3 York montage. Then from our connectivity, since the connectivity is somehow defined based on the phase differences, we know that for each frequency there is a relationship between the phase difference, the frequency itself, and the delay that this phase difference embeds. So what we try to do is to recover also the delay beyond this connectivity from the values of the imaginary part of the phase locking value. And nicely, we were able to recover these delays only in those trials in which we have a higher motor network connectivity. And specifically, we could observe that somehow, I mean, as somehow predictable, but not a given if you start from this kind of functional connectivity metrics. What we observed is that there is a shorter delay between left M1 and SMA in comparison to the delay that we have between left M1 and right M1. And these like values are compatible with the known like findings from the literature and from the TMS itself. So the idea is then that if we are able to assess this functional connectivity and maybe times delays from this functional connectivity, then this might help us in answering to the question when to stimulate. So in this case, I would say, okay, so we want to stimulate when we have the motor network up. So for instance, left M1 and SMA and right M1, and we will do that in such a way that we are not stimulating everything synchronously, but maybe we do the stimulation with some delay between left M1 and right M1, and with a shorter delay between left M1 and the SMA. So as a final and future perspective, of course, we need more, as we were discussing before, and we will also discuss in the next talk. We need more understanding of what the clinical models in terms of brain networks are, so that we will somehow able to also focus our attention not only on the motor network, but also on other important networks that will be the target of our stimulation in the future. And also, I think that you have seen the several simulations in this, like in this presentation, but I think that one step further can be made also in the framework of simulating brain activity, which is to also simulate the effect of the stimulations on brain activity. And maybe by putting together all these pieces, our understanding of the connectivity in terms of functional and effective connectivity, also guided by TMS, will be improved in the future. And with this, I'm finished, and I want to thank specifically all the people, the work of whom has like been presented in this talk, but also the C2BPIs and the whole consortium, which is really made of nice and brilliant people. Thank you. So, and as already introduced, our next speaker will be Pantelis Loomis, who will discuss about targeting the language network with TMS, which is also something that has great perspectives in the future.
Thank you, Laura. And I will start my talk about how to assess the human cortical language network for pre-surgical evaluation and research with assistance and through the perspective of connect-to-brain technological achievements. So how this can be done better with multilocus technology and EEG, and also using different kinds of modalities. And why it is important to map the brain functionally. So one very important reason is like surgeries. And it's very important to remove tumors, epileptical foci well. And the reason is that the brain is very complex structure. And the functional eloquence of the brain so far is based on anatomical landmarks, and this can be unpredictable. So due to many kinds of variability. So what is the perspective of neurosurgery and of its neurosurgeon is to optimize the extent of the resection and to preserve the quality of life. And neuronal organization has to be studied before. And what usually happens is that in surgeries, like the brain is studied at that point. So a priori information is very important. And this can be done with neuroimaging techniques. So the gold standard is that we have a grid electrode, subdural electrodes, or with which is called extraoperative. So it needs an extra operation. And this is usually for epilepsy. And for tumors, the neurosurgeon goes to the loquent area or in the tumor and tries to figure out whether there are functions there. So, and labels it at the same point. However, a priori information can be very useful. And so far it has been done with MEG first, fMRI later, and also DTI and diffusion tensor imaging, and of course so the MRI can help. The MEG gives a very good temporal resolution. So if you have a speech paradigm and object naming, it will show at which time different areas are active. while the fMRI will show with a bit better spatial resolution which areas are active, not when. And definitely there are limitations to all methods. The invasive mapping is for patients only, and it's defined by the craniotomy size. So there are many restrictions. It's of course very expensive. It requires very, very skillful people, and it's not available in all surgical centers. The non-invasive mapping is that MEG is temporally specific, fMRI spatially, and when they have been compared to invasive mapping, they had big differences, like they were not that reliable to be used alone. And navigated TMS has been proposed for speech cortical mapping because it has been used in studies of functional organization of speech. It has been used very successfully in motor mapping with the use of navigation, of course. And also it has shown that repetitive TMS can disturb ongoing speech activity already in the 90s. So that was why we used the TMS 12 years ago about in Biomac laboratory to show that it can be used. Some very fast, although Timo talked. What is TMS? You probably all know, but it's a non-invasive tool for stimulation, and it uses a magnetic field that it becomes electric in the cortex. So it sees the skull as transparent. And you can use it by, you can have a coil over the skull, and you can record activity from the muscles. Like with one pulse, by changing the coil, you can do mapping and get different muscle responses, and you can also place the EEG cap and get also EEG responses. Both EMG and EEG are very sensitive to the movements of the coil. So navigation is very important to reproduce and to know where you stimulate and keep it still to a specific spot. And also like the representative spots for motor activity, for speech and other, they are unique for people. They can, of course, like fall into the anatomical landmarks, but they are different. And that's why it's very important to do functional mapping with TMS. TMS is used in 3 ways. To study the electrophysiological and hemodynamic conducted responses. You can use to observe the behavioral and electrophysiological consequences of disturbing ongoing neuronal activity, which is what we do, and I will show with speech mapping, and treating patients, of course, with repetitive TMS as depression, stroke, rehabilitation, and other methods. So for mapping, it is very important to have navigation. We need to know where we stimulate. We need to know what kind of responses we evoke based on where we are. We need to reproduce the results which navigation allows us. And also a very big advantage of navigation is that allows the fusion of different kinds of modalities, like information from diffusion tertiary imaging, from MEG, from fMRI, from many other modalities like PET, NIRS, whatever its clinician or user wants to use. So TMS has been utilized in studies of functional organization of speech, and it has disturbed the speech successfully. By including all this, we have managed to create a method that is now actually used worldwide, because we managed to show that, like the community actually, to show that there is an error that is about 7 to 10 millimeters in comparison to the golden standard method, which is always compared to. So this was the first setup, which is not very clinical. And then you can see what is the coil, you can see what images to be used. Of course, all this have been standardized and become more like and normalized all things. Then you can see what is the coil. So, and this is how it has been commercialized, that they are all in one computer saved and without the need of extra cameras and extra connections. So the procedure I will show in video, it requires to find an intensity which is comfortable and also that it can reach the brain. And then we use like repetitive TMS of 5 pulses at usually 5 Hertz. Sometime after the pictures, about 300 milliseconds, and this is based on MEG work. And other groups use 0 milliseconds because that is closer to the gold standard way of doing things. However, like we are trying to focus on the speech-related functions only. And we repeat this several times. So, and we can map both hemispheres. We can map specifically the tumor, the perilational area, and whatever actually we want without the restriction of time and restriction of the craniotomy. So here is an example. So first we saw the images without like TMS. This is an old example. The images now are normalized and used in a standard way. So we are sure that the errors are not because of the images or of other parameters like lack of focus. So when they are only the ones that are well performed are used, and we move the coil until we find an error. Here is an error. The coil moved though. We go back and we find the error again. And then the experiment can continue. And you can use different kind of naming paradigms, object naming and action naming and many other things. And the objective is to create individual maps to help the surgeon design the craniotomies and speed up the procedures, to create a protocol with very good controls. We want, of course, like there are limitations. We want to diminish false positives. We want to keep the false negatives. We want to be more specific. We want to avoid non-responders. We would be very happy to replace awake craniotomy. At least we can have a complementary method and to give it to those that they don't have the awake craniotomy, at least. So now it's high time to improve this tool. And one way is to combine it with neuroimaging in a personalized way, again, that we will use MEG and fMRI of the specific subject, and we apply this information for the specific mapping of this subject. And then real-time tractography, as Timo showed, can be a very useful tool during the mapping to follow the fibers and find like to stimulate areas that are connected to the speech area, although they are distant. And the EEG can be also very important to help us to understand the effective connectivity and how the signal propagates and where and which areas are connected. And then we would like to apply Multilocus TMS alone or in the combination of the other methods. Alone, just giving 2 and 3 pulses on the same nodes of the network to avoid the lack of non-responses and to make it even more robust. So an example I can give, like by using MEG, we have an image, the subject responses. Here we see the different areas that are involved at different times. I can show here at 100, let's say 80 milliseconds, we have this activity about. Then at 200, it's similar area, but not that strong, and less strong later on time. So the activity, of course, of MEG continues, and we can use the different times just to map specific areas. Like, let's say that with 500 milliseconds, we would stimulate in this area mostly, and with 200 more frontally. So if we compare now the example that I showed, like, and we do a mapping, and we do a mapping by giving TMS 180 milliseconds after the picture onset, we will get 11 errors out of 87. If we use the default that we usually use 200 or 300 without knowing, we get less, 9 out of 107, and this can be considerable. And if, for example, we go to 215, we get even less. So this is something that, this is a way of personalizing. It's not that MEG exists to all centers, but it can help a lot, like personalizing the mapping. And then if we use also the tractography and the real-time tractography as Timo showed, we can, for example, do this. So this is from a project that we are trying to map supplementary motor area, because neurosurgeons have the problem that when they remove humors from here, they may get aphasias. So we want to see, and usually there is no speech mapping there. So we wanted to see how structural connectivity can help us. And here is an example that we are like doing during the mapping. We check, the cursor represents the middle of the coil actually. So we check whether there is areas like sites in SMA that are connected to the speech network. And here, this is one nominee, but as you will see, it is actually connected to the other side, mostly. And then if we move forward, we will eventually see a site that is connected to the speech network. So we did mapping of this area. And the result was in a similar way that we found here in SMA where it indicated the real-time tractography, we found an anomia with the red color is anomia, and we found also performance errors. And actually the shape represents also the shape, this shape. So the shape of the errors, like they are following this shape of the tractography, like the Aslan tract and how it is connected to the rest of the network. So EEG data can be also very useful. Here is cluster statistics comparing a protocol of 5 Hertz and a protocol of 7 Hertz, because also this play a role in evoking errors. And we see that there are both left and right hemispheres, like there are some significant differences in low frequencies early after the end of the pulses, because we wanted to avoid the artifacts, so we can study mostly 200 and 300 milliseconds after the stop of the sequence. And this can be also very useful for multilocus to see where we stimulate simultaneously, or priming the one area with one pulse and trying to disturb with the other or with other sequences. And this is actually where we want to go. And we want to create a fully embedded neuronavigator where we can have real-time the structural connectivity, but also the functional. also what I showed with MEG can be real time in the Neuro Navigator by moving the coil, highlighting which areas was at what time active. And we want to have a mapping with the EEG cap on, so we get more information with about the effective connectivity. And eventually we dream of guiding the mapping with the EEG recorded brain waves, although this is a very ambitious, for the moment at least, idea. And eventually what we want to do is to make the mapping very reliable and to be a method that it can be trustful all the time, and to be used also in centers that are very reliable, in centers that the awake craniotomy, which is the gold standard, does not exist. So very briefly, the idea is to use the a priori information, put it in the system. We do want to do it automatically. We do want to use the structural or the functional or the effective connectivity, which is actually everything, to guide the coil. And because like there is user dependence, TMS is very user dependent, especially mapping. So we want to come over these dependencies. And of course, this is a teamwork, many years in Biomag laboratory, nowadays in Aalto University in NBE, and through Connect to Brain, a lot of help and support in order to achieve these big ambitions. Thank you.
Thank you, Pantelis. Very, very interesting, and hopefully, I mean, soon doable with the system and the algorithms. So I don't know whether anyone has any question about the talks that have been given so far. I think in terms of time, we still have a few minutes. So maybe I ask a question to Pantelis, just I mean to focus my mind on what could be done on top of what he has shown. So if you had to pick one target oscillation to study the language network, what would that be?
Okay, this is a very, very tricky question. I would like to avoid it, like
sorry.
yeah, but I would think like, well, what is like our intuition is that that's why we use 5 Hertz and 7 Hertz to perturb the network. So some frequency 4 to 8 like Hertz, it's what I would think. It seems that something like this is that's why we can actually like create errors, but it is not that easy to do it real time. So for the moment, maybe the idea is more to see how different areas are like with the cluster statistics, we can decide where to use the multilocus TMS like simultaneously. And then we see how we can like use the real-time EEG to trigger it.
Okay, but still, I mean, with the slower frequency, there are more longer windows of opportunity if we want to put it in how Christoph was, I mean, putting it. So let's see, maybe.
Yes, let's see. And we are together in all this. So we are facing it already, and we see how it goes.
So I don't know, anything else from you guys? No. Okay, if not, I mean, I thank you again for being here and recording this session for the IOP attendees. And I remind you and the attendees that we have also a Q&A session that in which we will have the opportunity to answer the question that the attendees will have. And that's, I mean, so far it's scheduled for September 10th, but I will get back to you. Okay, so thanks again.
Thank you very much, Laura.
Thank you.
Thank you.